So where it looks like a different result, the final result is like this.
I think that's true.
Maybe
You see where
some of trigonometry technique you need use to make this. I think I still have this. The case of the positive. So you substitute this equation, right? This equation and substitute each individual term here. Then what we found is some terms I think cancel, so that's why the left side only this term, and right hand side become this is a product, so you can finally become this is a cotangent something for this. So where let's start from the same thing, which you start from here, right?
right.
So then
What I did was I factored out the
you already you factored
Cosine
out
of-
cosine. You do that first.
delta.
Okay.
Because I saw that on both the top and the bottom you can just get it out.
Yeah, sure. It's okay in term 20. Then if you're familiar with, I'm not sure this is square, so if you multiply
So
both.
this part I might not have
The camera
done the smartest thing, but what
That'd
I
be cool,
did
though.
was I factored it out,
because
And
it
then
is some kind
Maybe
of
some way.
had this
But
extra
I
10
don't think
square
that one,
term, so that way I can cancel this. I just thought it
Okay,
looked better.
that's
6
fine.
years
If I
old,
look
I think.
your step is correct, even though the
Maybe,
final
yeah.
the expression is not same, but that's fine.
Would this still be considered a transcendental equation
and
though?
Facebook.
This one is right. So here those are constant.
Yeah.
Because so when you do this way, it is not easy to see the curvature of
Yeah. That's
yeah.
what
That's why. So sometimes probably you do not do this before and keep it out. So that this is like two cotangent, right? So then you
Yeah.
can see the curve. Here you have denominator this cotangent. So if you know the cotangent this, like this cotangent alpha, cotangent beta, can combine to the cotangent or some sign alpha plus beta. If you can make that way, then finally we can make the functional looks like.
Yeah.
Whatever this is constant, but this
Did you
one,
see the homework?
it's,
Of the electric
it
magnet?
is, looks like
I glimpsed over it.
clouds.
I'm still working on homework too.
Or you move this to a term to the left hand side, so that is,
I would
then
argue,
it's-
to be
yeah,
honest.
then this is a constant, so
scared
that
from
is
this
the
course.
cotangent, tangent become cotangent, right? So this
Yeah,
can become
I am
cotangent,
too.
then maybe something comes,
But
right?
I
Yeah,
just
so
kinda
if
let-
your intermediate step is okay,
that's kind of like qualifiers
that
taken
is
away
okay.
of everything in my
But
life.
just
so
try
it's like,
to
I just
see
need- I just
how
need
to
to catch up a
manipulate
little bit.
your
With-
expression, make this,
Yeah.
make your final solution easier to understand.
I felt like with this, like the Newman equations
Uh-huh.
and the Bessel functions,
Yes,
there's just like so much algebra and trig.
yes,
It's hard to know what's the best next step.
yeah. So that is, I did for the zero, I worked to zero, just let you to try to mimic maybe the way that, so keep sine, cosine instead of direct go to the cotangent, tangent. That may be the one way, because sine, cosine, then sometimes you can cancel or can make a tangent. If you make tangent, if you're familiar with this addition or tangent alpha plus tangent beta or multiply, then that will be okay. Most cases we're familiar with sine, alpha, cosine, beta. That we are going to use that behavior. So that is the way. But of course, for higher, that's more complicated. The reason why I gave you equal to 1, equal to 1, I didn't here, I derived myself and I found, oh, okay, I finally get something similar like this equal to 0 case.
Yeah.
So, but yeah, that you are right, that how to manipulate such that we can make the final expressions simple. Do in a way, do not make some function square, right? Always not just not square, then you can make some cancellation or something. So if
it's the first order.
yeah, first
then it's
order is better
easier.
than the second order. Yeah, something. And then finally, sometimes some of do not move before you cancel. So left hand side, right side, after you make something, you find the some constant you can cancel. So that is, yeah, to do exercises. Okay, try to sign this, just a participation sheet.
Kyle, how
I
you
forgot, I asked you homework is today or on Wednesday?
I think Wednesday.
Wednesday, right? Okay, yeah.
Wednesday.
Wednesday, all
I
right,
think so.
okay.
Seems like everybody's hanging on after
After
qualifiers.
qualify, I know.
Like, it's way too early in the semester to be struggling this hard already.
Already started,
I feel that.
it's
Look,
struggling.
I had a meeting with Mrs. Fogg. I'll have to tell you about it.
You all are gonna have to tell me what that is at some point.
STEM,
When it will be qualified?
graduate STEM
Qualified.
outreach.
It was last Saturday and then next Saturday.
They gave me a lot of good ideas.
Or this coming Saturday.
Good luck for you. And everyone.
I'm trying to catch up. I'm tired of playing behind.
It also feels like we haven't been in here for like a week or something. It doesn't seem like a long time since our last class.
Going from Wednesday to Monday, it always kind of feels like a long time. But
I might be on the qual delay.
jet lag.
Kyle.
Jump jet.
I was waiting for it.
It seems like a long time
I
ago.
thought-
You don't get any sleep.
I thought you were going to Delhi or something about Rishi.
Rishi is very good.
He gave you a good second to try and catch it. Like he just stared at you for a minute like, catch up.
Well, he really thought I was gonna have something important to say. I was happy that we didn't have a meeting today
Today?
for the lab.
Okay.
I was happy that we didn't. I was
So next time, experiment.
Thursday.
Thank you.
At 2.
Two.
I think that's when we'll meet
We have meeting on Thursday.
Thursday.
And experiment on next.
I'm sure we'll talk about it on Thursday when we're available. Why did you want to do the experiment again?
Actually, to be honest, I was not prepared at that time, so
Now you feel more prepared?
well, I have time to prepare. I can manage. I have my exam. Yeah, so.
Got through it.
Maybe once I get through calls and get caught back up. I've looked at talking with me an actual physics grad student RSU. We can get apply for them. It's a small group, so $500 would make go for a minute.
You know, they were talking at the SGA, you were there, about how they have the beautification committee with painting stuff. That wouldn't be a bad idea. Maybe, I mean, once we're established, we can do more important things, but that'd be,
That's $500 sitting on the table. My understanding is it hasn't been wholly applied for. Maybe if it's just like an event a semester. Something for our students.
did you apply for the research grants?
Can't really think of what to spend it on. I'm trying to pretty much like data and open source stuff and just sitting there on your computer doing it.
Yeah.
The best I could do is like a travel break, but I don't have that
can see it is a little bit different.
It's not like I'm just like,
With materials physics, there's always something new that you can buy.
right. It's not like I'm just like, you know what? I need a Galaxy.
No, you have to-
$250 should buy me a Galaxy.
You have to buy the title of a name for like a star or something.
Hey, you find it, you name it. That's why Makimaki was originally named Xena Warrior Princess. And that's a fact.
Why did it change?
Because it's basically in the solar system, and the International Astronomical Union has very strict guidelines on what things in the solar system can be named.
If it was outside of the solar system?
What's outside the solar system is pretty intriguing. I once read a paper where all these supernova candidates were named after Harry Potter characters.
Astronomy is literally the Wild West.
You're not even wrong.
I think I used to hear right last time. Let's try to remind. We deal with the hydrogen atom. So we know hydrogen has a proton and electron. Electron move around proton. The interaction between the proton and electron is Coulomb potential, which is only dependent on the distance between these two. So in this is a two-particle system. So the total function will include this, the information about the electron, proton, and time dependent. So the time dependent Schrodinger equations with this, right? We are going to solve this. Then we look at Hamiltonian. Because Hamiltonian does not depend on time explicitly, this is Hamiltonian, right? And then the wave function we know can be written in the product of a spatial part and the time dependent part. For time dependent part, we already solved. This is a very easy, this exponential with the total energy here. So then this equation reduced to, we know one is solved this, another is only the time independent Schrodinger equation. The time independent Schrodinger equation only solve this wave function is only spatial dependent, but still the two particle function, right? Function RE and or RP. So solve this one, we do further. We analyze this Hamiltonian as a kinetic, total kinetic energy operator plus potential. Potential we know Coulomb potential, right? That is this term. But this one, total kinetic energy operator should be some two terms. Kinetic energy operator for the electron and proton, but we know this is a center force problem, so we can replace by the kinetic energy of center mass and plus kinetic energy we call relative kinetic energy, which is introduce a reduced mass, so a single particle move around this another one, right? Something like here. We take RP with the new center, so then another one is this you consider the electron, but it's a reduced mass move around the center. So with these two terms, then we can rewrite, because this one is only function of capital R, function lower r, potential energy only lower r. So that means these two parts only depend on the lower r relative position, and this is a center of mass. Therefore, we can analyze this spatial wave function can be further written as a product of this function only depend on center mass, product with the function which is depend on the relative position. So then when we have this, so we substitute into this one, right? This one, the right hand side, left hand side, we rewrite this way. So that is this, and the function with the product of these two. Then we divided these both sides, right? So this side we have ME plus MP, and divided. So now I have phi. And special part, and then here. Now I'm going to move this because here should be product this one, right? But here, since this only for the capital R, so I'm going to move to the front, right? Doesn't affect this. And that is first term. Second term, 2 mu. And then denominator is product. Numerator here, that one is only for the lower R, so it's the function phi as from capital R can put in front. Okay, so that is, I use vector here since later we are going to use spherical coordinates to separate R, radial part and the angle part. So this is not radial part, this is a vector, right? 3-dimensional. Okay, so that second term and first term minus. Now, only because it's divided equal to E, right? I divide both sides with product rate function. So now you can see here, this cancelled. Then the function further reduced to the first term is only the function of the center of mass. This function on R. The second term is only function of the relative R, right? Okay. Minus this term. Now we can see the first term only depend on, or only a function of capital R. Second, the third term a function of lower R. The last, the right hand side is a constant. So if this always equal, well, any function, right? So that means the first term, if I move the second and third term to the right hand side, so we have the first term equal to E plus this potential plus this term, right? Right? So now you can see left hand side only function of R, capital R. The right hand side is some constant and function of lower R. They will always be equal. So since this function is arbitrary, there's no any special. So if this is set phi always, then that's be equal to only constant, right? So I introduce a new constant. I'm going to say E capital R. Okay. Then you have two equations, right? First one is this one, minus h bar squared 2 1 E plus 1 P. Equal to ER, right? Here, I mean, because these are numbers, you use vector or not vector fine. But this is another vector, not E, right? So that gives us, I can quickly write down here since we deal with this time in chapter 4, one dimension is more easily. Here I introduce K, where is 2 and E plus P E over H bar. And this solution very easily, we know that is plane wave. The plane wave with some of this normalized vector is 2 pi over 3 over 2 is a 3-dimension. You can remind the in the chapter 6, the beginning, we deal with the Cartesian coordinates, right? So this solution is very easily, we know that is plane wave. So what that means, this is center mass. So for center mass, the Hygge item, if the center mass has a motion, but this motion of the characterized is only plane wave with this K here. If the initial energy is 0, that just stop there, right? So, and that is what we are not interested. That is just a loop, the total Hygge atom self move at center mass. And that is the interaction between proton and electrons in internal potential, right? So external has no any other. If you put in the Earth, you consider the gravitational potential, that is another term. But here, this is the central mass we have. Very easy to obtain. Now, the remaining part equal to this one, right? So now, that means now I'm going to move this to the, whatever, to the left-hand side. I move this right-hand side, this to my left-hand side. So then the second part is minus h bar square 2 mu, right? This is for relative function, function for the relative coordinates, minus e squared over r equal to e. I move to the move to this term to the right hand side, and so that e minus er, capital R, right? And now I'm going to introduce e lower r, another constant. So then this one is only this determinant equation for the relative lower r, right? So now we have, this is we are going to deal with. Okay. Now this e squared over r equal to now e. So E equal to the total energy is energy of center mass plus total energy of this the relative motion considered like a single particle with mass of a reduced mass move around. On the center is here, right? Move around with the R. So now the two particle system reduced to single particle system. Then we can deal with, right? And this part is very simple. So now this capital E capital R is nothing but the kinetic energy of, if you really want to write down here, kinetic energy. It is continuous, right? So there's no any restrictions of center of mass. Then this one is total energy, relative energy, or just total energy of the single particle, which we do single particle with the reduced mass mu. So the first one, we already got this solution, so that is finished. Now we are going to deal with this one. How to deal with this? It's still 3-dimensional, right? Only the difference from beginning is that this is one single particle problem. Initially it's a two particle problem, right? So now we go further. We are going to consider what we do with this 3D problem if the potential has a spherical symmetry. So the either way is not Cartesian coordinates, it's spherical coordinates, right? So now we are going to deal with in spherical coordinate system, right? So in this case, now we can, here, since potential only function radial part, but this, the kinetic energy part, we have two. So that, remember at the beginning of this chapter 3, when we deal with the spherical coordinates, we first deal with this one, right? Because this term, we're going to separate into the radial part and the angle part. If you remember, here, that is radial part. Now, here I use lower r, there's no arrow here, so that is only radial part. This is a 3-dimension. Plus 1 over r squared and over this angle, solid angle. Remember this? I just reminded, right? And then we introduce, we know the physical meaning of these two. One is correspond to the radial kinetic energy operator, another is angular momentum, right? So here I just rewrite in terms of the radial kinetic energy operator, PR, remember this, and this one is square You may ask why we do that. Since if we use this, we substitute here, you will see this equation reduced to only radial part, since the angular part is a function of this spherical harmonic function. Remember this for angular momentum. So because, then this one we can rewrite. So here, this one, you see here I have a minus h bar, so h bar here, h bar square cancel, right? So that is the radial part kinetic energy 2 mu plus is minus a plus here. This one is we have angular momentum h bar cancel, so we have plus angular momentum. Just remind you which and then this here, yeah, is here is fine. Okay, now I'm going to replace ER by E, since we are interested in this energy for the bounded hydrogen atom, not electron move around proton, right? So that means now we are not interested in the central mass. So to consider with other convenient expression for energy of ER, we use E. But this E is this one, right? Not that total. So okay, so when we come down to here, you will see here, this is radial part. This is radial part, right? So this one, we can analyze the wave function of the single particle with reduced mass in 3D actually can be separate or products of the radial function and with angular. Because this operator only depends on angle. This one operator only depends on radial, right? So because this, then we are going to substitute here. Then what we found is to keep continuum here, so I still keep continuum P R square 2 mu here. Okay, let me keep here. R. Okay. And then plus 2 mu R square in the denominator. Now L square R and minus E square over R. This one we just keep it. Just remind me how to derive to the radial differential equation. And the spherical coordinates, we found the angle part already solved. So then you are going to divide it. Okay, we don't need to divide it, but here, let's see this one. Can I erase this part? Okay. So this term, this one does not depend on angle, right? So L square applied, this is the eigenstates of the L square. And what it gives us? Let me divide it this way. Since I don't want to repeat the others, so now the second term is, I can take this R radial function in front of the L square. Then this is a
L
L
times L plus
1 by
1
L plus. Yes. So then
H bar squared.
it is, yes. H bar square, right? L plus 1. I still keep it. Okay. So now, you can see this side. This equation, the both left-hand side and the right-hand side, we have all the factors which is does not, because PR only we work on the R, right? Radial function does not do. So we can cancel this one, cancel the spherical harmonic function, cancel this, right? So now you can see finally we reduce this 3D time interval equation to only the radial part since the energy part already solved. So now finally, let me write down here that is, I still use PR. Then we are going to, if you remember what is PR, then we have 2 mu R, the first term, right? Second term is only function, so 2 mu R squared R, yes, R, mu plus 1 H bar squared, right? Third term, did I already? Yes, third term is R and E. Right? Now we have this. So you can see this is a radial differential equation, if you remember, right? Radial differential. That is the beginning of this semester we deal with. So now we are going to use PR, substitute PR into here. Sorry, I think I did something wrong here. This is not this one. I will use PR, right? So now I also need the PR, but you can find PR is 1 over R minus 1 over R, the partial okay. Whatever, you know that. So okay, now I'm going to replace PR. Finally, this equation is reduced to 2 ways. No, just finally. So finally, we have yes.
In the denominator, it's R or
Which one? This one?
that?
2 mu R squared. This is
no, numerator is fine, I think. Denominator.
yes. And because I already multiply here, right? Yes. And yes. Okay. And then that's all, right? Okay, thank you. So finally, we have this one. Partial R squared, partial function, partial R, plus 2 mu over H bar squared, E plus M squared over R, minus L plus 1 R squared. Okay, I just, because here we have a minus H bar something. Then that negative go to here become plus. This negative move to the left hand side become plus. So this is a term, is these two terms combined together. This one, H bar 2 mu also cancelled with this H bar here, so that's cancelled. Then we have this term. Right, this is a radial function. Any, right, we have not, the only difference here, the potentials in this case. Okay, now we are going to deal with start from here. Start from here, how to deal with or solve this radial differential equation. First, we only consider the bounded state. Consider this bounded state. Since we consider hydrogen atom that electrons still move around the proton, not leave away, right? Not ionize. So in that case, that means energy is negative. That is real. So for this case, let's rewrite this one, since we are going to deal with, for the particular case, that one's fine. Now plus 2 mu over H bar here, since this is negative, so I'm going to use absolute value. and minus x here, right? Since e is negative, so I have a negative multiply absolute value, then plus e here, square over r. Okay. This one. And minus L plus 1 divided by r squared. Equal to 0. Okay. So now, last time Kyle also asked me how do we know to manipulate this differential equation such that reduce to the complement hypergeometric differential equation? Yes. So the first step, usually you see we have a sum of numbers or constant here, right? We want to deal with the function such that those one just replace by one constant, so that makes the differential equation looks like more simple. Do not confuse those constants. So to deal with, you can see here, I'm going to introduce some constant to replace this one, right? So define, that is manipulate or clear up this equation, the first step. Define alpha square is, that is 2 mu absolute value e, okay, or h bar square. This is alpha square. But then you say, I have another term, yes. So we are going to introduce another parameter to replace this one. So here, you see this term is 2 mu e square over h bar, right, square. If I define this alpha, so that's be also related to the alpha and another one, right? So now I'm going to introduce, define this alpha beta, is this one multiplied here, but we have this term, so we have a divided. Alpha beta is this, keep factor 2 and keep the factor 2 here, right? Alpha beta equal to over h bar squared. So, okay, then we can, from here, we can define what is beta and then look these terms. Okay, then you can see here, this term, mu h bar squared, right? And equal, so this is nothing but alpha beta, right? So here, but finally we need beta, so I'm going to also from here you can see beta is mu e square o or square root, because it's alpha squared. Alpha squared, so now I'm giving it. Alpha beta is oh okay, yeah. That's right. And then beta is h bar square alpha, which is alpha here, right? So you can see alpha square is this, so the alpha take the square root. Then there are terms h bar, so here I give finally beta is e square over h bar square root mu over 2 absolute value e. So in this way, now I can rewrite here. This one is 1 over r squared plus u plus r squared plus u. R. The first term I still keep here. The second term is plus minus alpha squared. Right? The first term we have minus alpha squared. Second term, this is alpha beta, but I have factor 2 here, so that is plus 2 alpha beta over r. And you say, okay, still have a 2. Yes, later we are going to eliminate alpha. So later, that is the second step, right? First step here. Then this one still keep here, right? L plus 1 r squared. Okay. So looks like this little clearer than this one, right? Now next step. So next step is we want to rewrite this formula or introduce another variable such that one of them we can cancel. Then how to do that? You can see here we have alpha squared. So I need this is also alpha squared. If I introduce another variable which is a sum of constant multiple alpha multi r, then it maybe can cancel this one. So define low is 2 alpha r. Okay, this way we can reduce the alpha. Let's see how to do that. We okay. Okay, now if I take low, so I need this become a low, then I need 4 alpha squared, right? Denominator and numerator 4 alpha squared. Then here, the 4 alpha squared must come to here, so that is a low square. Then here, this one, I need another alpha, right? 2 alpha. 2 alpha, 2 alpha become a low, right? 2 alpha, 2 alpha become a low, so you have alpha squared factor there. Here I have alpha squared, and then this one, if I multiply 2 alpha, then I have alpha here, alpha squared, and factor 4, but 2, 2. Here also multiply, so then you will see you have alpha squared both, we can cancel, so now let's do that. I'm going to, so now 4 alpha squared, so 4 alpha squared r squared, right? So I multiply and divide it. Partial here, that is also 2 alpha partial 2 alpha r. So I multiply also divide it. And then inside is alpha squared. I don't need it because I'm going to observe this one inside. And then here 2 alpha partial r partial 2 alpha r. So I also multiply and divide it. Okay, so that is first term. Then the second term, this inside minus alpha squared here plus 2 alpha beta. Now I want to multiply or divide this one here in the denominator, so I have to multiply here. Then this one, similar things. I have 4 alpha squared L plus 1, 4 alpha squared R squared. Okay. Now this is low square, this is low, and this one go to here, low square, so this is low, but I have 4. Let's keep. So first one is 4 alpha squared, right? This one, this one. And then here, partial row, and row square. This is row square. This row, right? And partial here inside. This one comes here, so this is row square, partial r row instead of r and replaced by row. That is first term. So the last term we have, let's keep it, we have minus alpha squared plus, it's a 2 alpha, 2 alpha, so 4 alpha squared, right? 4 alpha squared beta and rho. The third term is here 4 alpha squared L plus 1. Denominator is rho squared. So now you can see I have all the alpha squared here. Or 4 alpha squared. This time, here, 4 alpha squared. 4 alpha squared. This one, if I take 4 alpha, I have divided by 4, right? Then we can cancel those terms. Then you will see only the beta, no alpha. So now, when we have only one constant, then we can go further. So this is the first step. Try to clear up the equation or make the equation more simple, right? Or that is, so finally we have, and now here, finally we have a partial square. We have two, and then this. The first one is this one, right? Partial row square, partial r, row, partial row. I divided up this 4 alpha square, so then the second one is here, right? We have a factor minus 1 over 4. So plus minus 1 over 4 plus beta over rho plus minus L plus 1 whole square r rho equal to 0. Yes. So now you can see I only have rho, beta, alpha disappeared. Okay, so that is over. I'm going to say this equation because sometimes I use this equation, sometimes I use another one. So they are equivalent. Another is I'm going to make this partial derivative inside, right? So this one, if I keep this low square is and put to the partial, the second order, then low square cancel, right? So another expression is square. Second one is keep this one, but do this, we have factor 2. 2 rho, and then rho 1 is, so we have 1 over rho. And 2 over rho partial, the first order. And the remaining part same. Is the second part is 3 terms of same, keep the same. So I'm going to say option 2. Both are okay. So this is the equation we are going to start to deal with. And what we are going to do, we are going to find what is R, right? How to do that? No boundary condition. And as I said, if the potential no boundary condition, the so-called boundary condition is we analyze the asymptotic behavior. When rho go to 0 or go to infinity, since the function itself be finite, right? So first, so that's the second step. First step, we just try to manipulate this differential equation, make this more clear or more simple. Then the second one, we're going to analyze behavior. That is second step. So first one, okay. Let's see that when rho go to 0. Okay, when rho go to 0, that's why I like to do this. You can either select this one or select this one. So you select this one because we have this one is a little bit make this because we do not know this one how fast how small depend on this rho go to 0. So we prefer use this one. This term we are going to keep and only look this term. And in this case, this constant, this is first order, second order. So this one is dominant, right? Okay. So from equation 1. So that is why I use equation 1, not equation 2. But for second case, I'm going to use equation 2. For equation 1, so we have 1 over rho square partial rho square partial r partial rho. This term keep. This one is my job. Minus L plus 1 rho square r rho equal to 0. Okay, so to solve this one, if you are more experienced, maybe you have the solution. If not, let's just like testing function. So solution, what type of solution? It looks like R, so is something like this linear combination of rho to the L's power with some constant A plus second term is rho to the minus L plus 1. You may say why? Well, yeah, let's try. If you do not believe that, let's do that. So I think you can try. Let's see. I ask you to try yourself. This takes time. So check your cells. How to do that? Very easy, right? So your R is this one. So you just need what you need here. You need to find what is partial R, partial rho. Equal to how much, and then you look this one, you put how much, and then you're going to substitute this one. You will see that is and this one is equal to L plus 1. You will prove that, and then so that this term equal to that, so that cancel equal to 0. Just check yourself. Okay. Now, this is to give us at the rho go to 0 is we have this behavior. However, as I say that we have to have this radial function to be finite. So when rho go to 0, this term is diverse, right? So physically, the R's we only, okay, I think only this term, right? To the L's power. Because second term, this is considered when rho go to 0 case, so this goes up. So we have to drop that term. So only one behavior when the low go to infinite, go to zero, that the asymptotic behavior of this R low to be follow low to the S power. Okay, that is first case. Then we consider when low go to infinite. In this case, I'm going to use the equation, second equation. Why? Here, when low go to infinite, this is still complicated. But now, here, I need to keep this one, right? But this one, when low go to infinite, this one, we can also drop. Only this constant makes sense, right? So we have this solution we know, right? Since this minus must be exponential to be positive, not imaginary, to be real, right? So the solution, mathematically, solutions be like this. As exponential is a positive or negative, then we are going to drop one of them, right? Rho is proportional to plus minus. That we really, because this 104 is 102 squared, right? So that is a factor like a k squared. Then you also have solution. If this minus, this is plus, this is I here, right? This plus, minus is real, right? Okay, so then again, physically, we need physically acceptable. We need the low go to infinity to be converted, so only negative one, right? Acceptable is we have to drop the positive one because the positive, the low go to infinity is one. All right. So when we have these two asymptotic behavior, now we have the behavior at least we know is be enveloped by these two, right? So then, so finally we have the R must be have this relation. Not equal this. Follow this, right? So rho to L's power control. This is a, like I said, envelope to control the rho go to zero. Then the intermediate function I'm going to introduce, which we do not know F low function. Then the right side of the envelope is controlled to the low go to infinite. So that we analyzed, we have the radial functions we follow this. Then we are going to next step. So you see, first step, clear up this equation. Second one, we're going to analyze it as asymptotic behavior. Third one, when we have analysis, so now we are going to substitute this one into this differential equation, and then finally you will find the differential equation for F low. So that is the next step. All right. To substitute this into here, which equation we use, I'm going to use this one. Since here, you can either use this one, but I mean, I'm going to select this one. So this is first order, second order. So we need to do the partial derivative, right? So in order to do this one, let's look this first term. Let's first look at this term because we have three terms. 1, 2, 3, right? The first term or the third term. Look the third term of equation 2. So that is minus 1 over 4 plus beta over rho minus L plus 1 over square, right? R rho. Then R rho is this one. Okay, so I'm going to multiply inside. Since finally we are going to cancel. So what I keep this outside, only this one, because this is only the powers, right? So that will change. So then the first one is minus 1 over 4 rho to the L's power, right? Second one plus beta and the rho to the L minus 1 power, right? This L's power we have a minus 1 here. The third term is minus L plus 1 rho to the L minus 2 power. Okay. That is the third term. Now let's look at the second term of equation 2. Then we are going to substitute together, right? Put them together. Second term let's first, that is 2 over rho partial r partial rho, right? So let's keep this one, and we are going to do derivative. We have 3 terms, so we need to have 3 terms, right? So partial derivative, first do this one, let me see first, which one? Yeah, first do this one. So we have rho to the L's power, partial f rho, partial rho, and exponential. And do second one, I'm going to do this, keep this one, so that L rho, L minus 1, f rho, exponential, and then keep this 2, do this. When we do this, we have a minus half, right? So minus half of this one, and then the same thing, rho to the L's power, f rho, exponential. Yeah. Then I'm multiply this together inside, and then I'm going to take this exponential outside, right? So that is factor 2 here, and then there's a rho, L minus 1, right? And partial f rho, partial rho. I keep this exponential outside. So that is the first term. Second one is 2 factor plus, still I have 2, and then L, here we have 2L rho, L minus 2, right? And rho minus, so 2 cancelled, and here rho, L minus 1. Okay, now I'm going to, because we have 2 terms, so now combine together. This one, 2L, this is a 1, right? So that is plus 2L minus, oh, sorry. Okay, keep that one, 2L, keep rho L minus 2, because they are not in the same power, minus rho L minus 1, and rho exponential. Okay, that's second term. Now we are going to deal with the first term. The first term is a bit complicated since we have second order derivative. Now let's go to first term. Equation 2. That is a second order derivative. Since we have a first order is this inside, right? So what we need to do is, first order we already have 3 terms, and each term will have 3 terms. So actually we have totally put 9 terms. Okay, so just carefully do it. I'm going to write down these 9 terms rho. For example, here I do this, keep this one, do this one, so we have a second order partial derivative of f rho. Partial rho square, keep exponential. And then second one, I'm going to do this, so we have L rho, L minus 1. Still this one, partial f rho. Partial rho, exponential, and then we keep this to this one, so we have minus half rho to the L partial f rho, partial rho, exponential. All right, so this 3 term is this one. Now I go to this 3 term. This I first do this one, so that the L rho L minus 1 partial f. Second one, I do this, so we have L minus 1, rho, L minus 2, right? F rho, exponential. Then keep this one, so we have a minus half L rho. Half L rho, L minus 1, F rho, exponential. All right, so 6th term. Now the last one. Last one, I still do the ones first to the half of rho to the L's power and the partial f rho, partial rho, exponential. Second one, do this one, so the minus L or half rho, L minus 1, f rho, exponential. The last one is minus half minus became plus, factor 4. Okay, now I have 9 terms. And just combine those together. So we will have second order derivative, then we can cancel each other. Let me cancel. This one here, right? So, okay. So
Dr.
now,
Yu,
yes.
when you have this e to the minus rho over 2,
Uh-huh.
is that still need to be differentiated?
Yes, this is a function law.
Okay.
This is too low, right? Yes.
So we
now,
have to do the chain rule. I was just
yeah,
making
yeah,
sure.
that's definitely, yes. So now I'm going to summarize. So the second order part is low to the nth power, exponential, half rho, and half square and rho, square. And the first order is 2L, L, 2L rho, L minus 1, minus rho L power, and exponential half rho, and the first order. And the zeroth order is L minus 1, L to the L minus 2, minus L to the L minus 1, plus quarter L to the L exponential and okay, now we can try to see which one we can cancel, right? So now you see the third term, let's look first, so first term, let's look this zeroth order, right? Zeroth order, here we have zeroth order. So you can see here I have this term, negative, this plus. So they cancel, right? Okay, and another one is this term, L minus 2, this one. This one, okay, this one has something. So L minus 2, here is L plus 2L, right? So we have, yes, I have, this one is 2L, L minus 2, right? L minus 2, but I think we have another one, L minus 2 here. This is L minus L plus, so this is minus L squared minus L, right? And here we have this positive L. So we have this one, L squared cancel, this minus L. So positive 2L, the minus became a minus L, right? And this one is canceled. That makes sense? So we have this term, and this term canceled. Let me see some other. I think the first order we do not have, we can combine. The first order we have L minus 1, this one, right? But this factor is not same, so we keep in mind. Okay, so by such, then finally, the final result for this equation, just substitute those together. Hope you understand that. So finally, we just substitute first, second, third term to this one. Then we have rho, and also since we have a rho to the L's power, L minus power and exponential. So I all cancel L minus power. Then here we have L, one low, right? So here I have one low, and this canceled. So let me do this one. Cancel this factor. Then we have rho. Second order, this one, because we cancel, so we still have this. And the first one, the first order here, 2L, we have another L, right? So that means that is plus 2L plus 1. Okay, 2L, that's 1, right? So this is all L's power. So this is just a constant here. And then this one, take off the L minus 1, so we have no, right? And the remaining part constant only this term. Not this term, we have also beta here, this term. And this term, right? Okay, up to now, remind you, what is the Compton hypergeometric differential equation? We may combine together, right? Differential equation. Some you learn, some not, so I just learned. But in general, it's like if your variable is z, d square f z dz square, and plus constant b minus z, the first order, and then the minus constant a multiply f z equal to 0. That is a general component hypergeometric equation. So from what we just derived, analyze the asymptotic behavior of R law, then we finally found the differential equation for the F law. Now you can see here, this one, first order, right? Variable multiplied second order, so here compare this one, and this one, if we, this is a constant, so if I define this B, then that's B minus this one, and this A, those are all constant, right? I can define A. I give you a solution, right? So solution, general, right? That's Z. Yes, I gave you before, so now let's try to remind you. Infinite, and this is we call the Ricci factorial. A as B and the function S, and Z to the S power and S factorial. A S will be as same thing as 1 multiply A multiply A minus 1 and Q multiply A minus S minus 1 plus S minus 1 plus S minus 1. E is also similar things. E plus S minus 1. So correlation factorial. Okay, that is general. General, so that's what you need, just know this much enough. Okay, so finally when we have to reach to this differential equation, just compare with those. Then here in our case, right? Our case, how to compare with this? If we define B is 2 L plus 1, right? A is L plus 1 minus beta. Define, then we have rho partial over, because it's only function of rho, so you can use partial over total. E minus rho, F minus A, and 0. So we immediately got this solution, since that's B, the solution from the common hypergeometric differential equation, the general solution we obtain. Okay. Yeah. So the function, now we have solution F rho B, the function of, this is a common hypergeometric function. That's be A. A is here, right? A is L plus 1 minus beta. B is 2 L plus 1. And the variables rho, right? Okay. So that is. Now we are going to, once we have this, right? So we are going to so then here go back to, remember the R rho, which is rho. The rho go to 0, controlled by this, multiply F rho, and rho go to infinite, controlled by this, right? Then you just substitute here. So now in this case, we are not finished, because here we need to double check this one again. When rho go to infinite, F rho is go to follow this because you can see here. This is a constant, right? So this is like an exponential function. So R rho go to 0 if we use this infinite, the summation go to infinite, then we will have L minus half L is go to the plus, that's plus R. So we cannot be accepted, right? So even though we get the solution, but we still need to double check. So if it's still not finite, then what we have to do? That is not. That the problems come from this infinite summation series. So now if we truncate, become a finite polynomial, it's finite. So we have to truncate. From infinite series to finite polynomial. That is the next job. So how to truncate? That is, we have this summation. Okay. Now, okay. So just this one, right? So I think here, later I'm going to replace this A and B. Here, just S from 0 to the S maximum. F, A, B, right? So now we are going to truncate S from 0 to the S maximum instead of infinite. And same thing. How to truncate? That require, if we do this, it will automatically truncate, right? Requires A, S. This one should be finite because go to that over. But go over, the next must be 0. If the coefficient when S go over the X max, all the coefficient 0, then there's an automatic truncate, right? So that is required this one. And then what that means, if you remember here, this is AS. So AS is this product. So AS max plus 1 is A here plus S max, right? Okay, plus X plus 1 minus 1 equal to A plus, oh sorry, AS max. That's only last term control, right? The last term, that means this one should be equal to 0. Okay, this one is A. This cancels with plus S max should be 0, right? Then we have the result over. So the condition for finite R is A equal to negative S max. Because that A plus X max is equal to 0. So we are going to, what is A? A is here, right? So, okay. This come to, okay. That means A is L plus 1 minus beta equal to minus X max. So now I'm going to define or introduce, because we can define in R. See, this be an integer number, right? This is summation. S from 0, 1, 2, 3. So those are integer numbers. So I introduce NR is integer number. Integer, right? So that means minus NR, right? Then, very interesting from here, we can define this one. Okay. And what is the beta? If you remember, beta related to the energy. So in this way, we can find energy is quantized and how to determine the energy. So now I'm going to move the beta to the right-hand side. So now, on the right-hand side, beta equal to L plus 1 plus NR. Now, L is a number, so now let's review this one. This is integer number, L from 0, 1, 2, 3, and NR, okay. NR is 0, 1, 2, 3, all this integer number, right? So, this beta must be also in integer. I'm going to introduce another number, N. Right? Okay, so now, if I introduce beta equal to n, and because beta, if you remember beta we introduced is E square over h bar mu over 2 absolute value E, right? So that's equal to, okay. So from here we have the absolute value energy at x square root. Then you will see that comes down to here, so that is E to the fourth power mu, and okay, 2h bar square beta square, right? And then beta is n. So now you can see this energy is not continuous, not arbitrary. We have to quantize. So finally, I'm going to remove this one because it's absolute value. So now I'm going to remove this energy of, what is energy? Remember, total energy of the relative motion of consider single particle is reduced mass. I'm going to introduce index n because that depends on n. So now from here to here, and it is negative, right? I'm going to take the next sign. And then e to the fourth power mu 2h bar square n square. So this is quantized. And n we call the principal not quantum number, right? Number. So you see, very interestingly, just like by products, we have this energy obtained, which a lot of energy we know that we quantize, and that makes sense since for bounded states, energy is being discrete, right? So now we discuss n. N equal to L plus 1 plus NR, right? Okay. So n, if you remember n, the smallest n is which number? L from 0, 1, 2, 3. NR lowers 0, 1, 2, 3. So when L smallest number is L equal to 0, NR to 0. So n smallest is not from 0, from 1, right? And then the remaining when L equal to 1, NR to 0 is 2, right? Or NR equal to 1, L equal to 0 is 3. That is what's allowed n number, okay. All right, so you see this is this truncation does not mean it's just mathematically, right? It is physics in there because physics require the function be finite, and that gave us this. Okay, and the next Wednesday I'm going to continue to discuss this energy and also this energy, then the wave function that look like how to get interoperability. Then we are going to consider put the hedging atom into the wrong field, that is Zeeman effect, how to discuss that Zeeman effect. All right, so remind you that it is possible homework on Wednesday, right? Video. Okay, good. That help you to how to.
I'll have to play with it a little bit, I
Okay,
think, but
yeah, yeah.
I mean,
think-
having a definition for it at least cannot not help, you know?
Go back to also
See
the
it for the third time.
isotropic harmonic oscillator, how to derive that to to this case. Yeah, and compare these two cases. Maybe some of the idea. Okay.
Seeing
Yeah.
it for the third time
For
helped.
sure.
Helpful.
Okay. I mean, this class is since you are a graduate student and it's a second content, so we need more deep, right? Mathematic tools and sign notification or.
I'm excited to start adding in the spin.
Yeah, that is next job. we will actually maybe Wednesday we can probably can finish chapter 6. Then we go to chapter 7. Spin in chapter 5 we already introduced, right? Chapter 7 we are going to consider rotation and in general the spin and the rotation together, addition of momentum. Then chapter 8 we are going to consider the many particle system. So far the only single one.
Then we'll go back to statistical mechanics.
I think we will not have time this. Is that be in the Dr. Smartish?
Yeah.
Content, yes, that is it. That is last semester, you did, right?
Yeah, we're done
So
with
the
that.
before this. Yeah.
Oh. What do you all think you're going to do your presentation on? Rishi?
I haven't decided
Charter, do you know?
same thing with me.
Still considering?